Color space is a specific organization of colors. In combination with a physical device profiling, it allows for reproducible representations of color in both analog and digital representations. A color space may be arbitrary, with particular colors assigned to a set of physical colors.
Okay, now that you've Googled the meaning of color space and seen lots of graphic designers and videographers explaining how it affects their world, allow us to explain to you how color space fits into the world of Pro AV. Put simply, color space is the range of colors available to a video system. The camera captures an image using its particular color space. These colors are in turn transferred to the display so we can see them. So, think about your display. After all, it's the display that you're watching, right? In Pro AV world, we've historically heard color spaces described as component, RGB, and in recent years, HDR. But how do they differ?
Let's begin by looking at a typical chromaticity chart. This colourful arc-shaped area represents all the colours the human eye can see. If every display were able to show this amount of colours, things would be nice and easy. However, they can't. So clever people have written standards over the years to allow display manufacturers to work to. We begin with a little history. When standard definition TV first became digitised, the standard used to define the colour space it would use was Rec 601. We can place a triangle at the points representing pure red, pure green and pure blue as defined by Rec 601. The triangle formed between these points is called the colour gamut, and the area inside it shows us all the colours that can be displayed in a Rec 601 system. Any colour outside this triangle cannot be displayed in Rec 601. We can immediately see the limitations of colour for this standard. If the camera used to capture the image recorded colours outside this gamut, the display simply wouldn't have been able to show them, and that could result in a much flatter, duller image than originally captured. A few years later, high definition came along, and this worked to a newer standard called Rec 709, giving us a slightly different gamut than Rec 601. Rec 709 provided different luma coefficients or lighting parameters, which in turn meant that a different palette of colours were available to the screen.
This pleased the filmmakers because now their equipment which captured large amounts of colours were able to be displayed on higher resolution screens. Finally, when ultra-high definition hit the market, yet another standard was introduced called Rec 2020, and this gave us a much larger colour gamut. There were, however, still some issues. If at any point the original Rec 2020 video was compressed into Rec 709 to be distributed, to then be displayed on a screen capable of showing the Rec 2020 gamut, once again we saw flatter, duller images than if the Rec 2020 standard was maintained from start to finish. This is one reason why it's important to understand how the colour space is managed across a distributed system. We can clearly see that the Rec 709 image will fit perfectly into the Rec 2020 gamut. However, in order to put a Rec 2020 image into the Rec 709 colour space, there will be colour casualties. Okay, so now we have our three colour gamuts which represent the journey from SD to UHD. What is the difference between RGB and component video? Historically, RGB was used extensively in computing, as it was really easy to represent colours across the screen by varying the individual values of red, green and blue which would be shown. Component video is more complex. It keeps the luminance and chrominance of the image separate and has been continuously evolving over time to bring us the brightest, most intense colours we've ever seen on a display. HDR is a good example of this evolution, and that is a separate SDVoE Academy course which we would recommend that you watch.
If we place the RGB gamut into our chromaticity chart, we can see it's smaller offering less in terms of colour than that of the original 601 gamut. This made component the better choice for TV, and as component has evolved over the years, we are now able to see more colours on a display than ever before.
Now we've looked at colour space, let's turn our attention to colour depth. The best way to explain this is to imagine each individual pixel on your display can display its own colour or shade of colour. In order to work out how many different shades it can display, we use something called bit depth. Bit depth takes us to the good old days of binary, using ones and zeros to calculate a value, depending on how many bits we choose for our bit depth.
The bit depth of our pixel is usually either 8 or 10 bit, and this has been the case throughout each colour space from Rec 609 days. So, let's take a look at how we calculate the amount of colour shades available to us with an 8-bit colour depth. 8-bit means that we have 8 binary values available to us, and each bit represents a value starting at 1. Binary values can only be a 0 or a 1, so 2 values in total. Therefore, as we move along each bit, we multiply the value of the previous bit by 2. When we get to the 8th binary bit, we can see the value it represents is 128. Now let's work out the maximum possible value we can obtain by placing either zeros or ones above the line. The maximum value would be represented like this, which means if we add up all the values underneath, we get 255. Don't forget, 0 is also a value, which we would get by placing zeros across each bit. So the total amount of values represented by 8-bit is 256. Now let's apply this to each colour. So 8 bits for red, 8 bits for green and 8 bits for blue, giving us a total combined value of 16,777,216 colour shades per pixel, which seems like a lot, but let's see what happens when we make each pixel 10-bit. By adding just 2 extra bits, we now have a total of 1,024 shades for each of the red, green and blue values, giving us over 1 billion possible colour shades per pixel.
This difference comes into its own when we see vibrant and intense colour changes on a display, especially where many shades of the same colour are shown. With more colour depth, we have many more shades and a much more realistic image. However, the trade-off with a higher colour depth is that it does require more bandwidth, which we will discuss in the chroma subsampling course.